All right, if you're taking AP Physics, listen up. We're going to tackle one of the absolute classic traps that trips up so many smart students. It's all about the direction of acceleration. But don't you worry, by the end of this, you are going to have this concept down cold.
So let's just jump right in with what feels like a super simple question. You've got an object, it's moving to the right. So which way is it accelerating? I mean, it's got to be to the right too, right? It seems obvious. Well, in the world of physics, what seems obvious can sometimes be a bit of a trick. The real answer here is, it depends. And this is a perfect example of where our day-to-day gut feelings can actually lead us astray. And here's the core of the whole mix-up. Your brain just screams, hey, if it's moving that way, it's got to be accelerating that way. And look, sometimes that's true, but it's not the whole story. In physics, the direction something is moving and the direction it's accelerating can be totally, completely different. So how do we nail this like every single time on the test? We use what I like to call physics golden rule, and it's all about a really simple shift in how you think. You need to forget about which way it's moving, and instead, you need to find the force.
And that leads us to the hero of our story today, the net force. Now, this isn't just any old push or pull. It's the grand total, the sum of every single force acting on that object all at once. You can think of it like the final winner of a big game of tug of war.
And here it is. This right here, this is the one sentence you need to burn into your brain. Acceleration always, and I mean always, like there is zero exceptions, points in the exact same direction as the net force. That's it. It's an unbreakable law of the universe. You find the net force, you found the direction of the acceleration. End of story.
Okay, talk is cheap, right? Let's make this feel real. We're going to put that golden rule to the test with a really simple scenario. I call it the box tug of war. So let's imagine a box just sitting on a perfectly smooth surface. No friction, nothing to get in the way. We're doing this so we can really isolate the forces we're about to apply and see what happens without any other interference. All right, here comes our first player. Someone comes in from the left side and gives the box a steady push with 10 newtons of force. That push is trying to get the box to move over to the right. But wait a second, it's not going to be that easy. At the exact same time, another push comes in from the right side, pushing back with 4 newtons of force. So now we've got a little battle going on, a tug of war. Who's going to win?
And that, right there, is the key question. Before we can even think about acceleration, we have to find out who wins this tug of war. Or, in physics speak, we need to calculate the net force. Luckily, physicists have a super simple 4-step recipe for this that you can always rely on. First, you draw out all the forces. Second, you pick a direction to call positive. Third, you add up the forces. And fourth, whatever you're left with, that's your net force. Let's do it.
Okay, step 2, let's just make a rule. We'll say any force pointing to the right is positive. That makes our big 10 Newton push a plus 10. And since the 4 Newton push is going the other way, to the left, it becomes minus 4. Now for step 3, we just add them up. We're going to take our positive 10 newtons and add our negative 4 newtons. It's really just simple addition, as long as you keep track of those signs. And the winner is plus 6 newtons. That little plus sign is so important. It doesn't just tell us the strength of the final force, it tells us the direction. The overall net force is 6 newtons pointing to the right. Okay, awesome. We found the net force. Now for the final, and honestly the most important piece of the puzzle. Connecting this number back to our original question about acceleration. This is where we really start to think like a physicist. So let's be absolutely crystal clear. The tug of war is over. That 10 Newton push totally overpowered the 4 Newton push. The final, resulting overall effect on this box is a 6 Newton push to the right. And now we bring back our golden rule. You know what it is. Acceleration follows the net force. So if we just figured out that the net force is to the right, then that means the acceleration has to be to the right. That's it. It's really that simple. It doesn't matter if the box was already moving left, or if it was moving right, or if it was sitting still. The moment those forces are applied, the acceleration snaps to the direction of the net force. Let's look at this chart to really lock it in.
When a car is speeding up, okay, easy. It's moving forward and the net force from the engine is pushing it forward. But think about when you hit the brakes. The car is still moving forward, but the net force is backward, right? So the acceleration is backward. And the craziest one, a ball at the very top of its arc. For a split second, its velocity is 0. It's not moving. But is gravity gone? No way. The net force is still down, which means its acceleration is still down.
So let's wrap this all up. What do you absolutely need to remember? Number 1, get that idea out of your head that acceleration has to follow motion. It's a trap. Number 2, and this is the big one, acceleration always follows the net force. So your game plan for any exam question is simple. Find the direction of the net force first, and you've automatically found the direction of the acceleration. That's the key. Okay, let's leave you with one final question to make sure you've got this. If you throw a ball straight up in the air, what's the direction of its acceleration the very instant it leaves your hand? Well, it's still moving upwards. Just think about the forces. Think about that golden rule. You've got this now.